Hi, welcome to our talk. Our talk is Optimal Pricing of Information. This is a joint work by me, Weiran, and Haifeng. The paper is in precedence of ACM conference on economics and computation. In this paper, we will address the problem of how to sell information optimally. In our model, there is one information seller and one information buyer. The information seller can be the credit report company which holds the credit report of the loan applicants, and those information are valuable for the loan company. Or the information seller can be the house or the car inspector who knows better about the conditions of a car or a house, and they can sell those information to their customer. And in financial markets, the investment advisor knows better about what is the right portfolio, and they charge commissions from the client. So a natural question will be how to sell this information optimally. And this is what we are going to address in our talk. So in our model, there is one information seller and one information buyer. The buyer is a decision maker facing a binary choice, a passive action 0 and active action 1. The active action can be approving a loan, buying a house, or investing a stock. The passive action derives utility 0 with lots of generality, and the active action will derive utility VQT, where in here T is the buyer's private type, which is public known drawn from a distribution FT, bounded by T1 and T2. And the seller knows the public distribution F, but not the realized T. Q in here is a random state of nature which is unknown to the buyer. Q is public known drawn from a distribution G, where Q, T are assumed to be independent. And in here, the seller can observe the realized Q, but the buyer only knows the distribution G. Now, let me give you a concrete example. In here, the buyer is a loan company deciding whether to approve a loan or not. If not approving, which means action 0, the loan company will derive utility 0. However, if approving the loan, which is action 1, the loan company will derive utility VQT equals to Q times T minus 2. And we can understand Q as the payback rate, T is the gross profit, and minus 2 is the operating cost. For example, if the Q is known drawn from uniform distribution from 0 to 1, and the realized Q is 1, and realized T is 3. So from the seller's view, VQT equals to 1 times 3 minus 2, which is positive 1. However, from the buyer's view, since the buyer only knows the distribution of Q, the buyer will calculate the utility based on the expected Q, which is negative 0.5. Thus, under this situation, the buyer will reject this loan and miss a chance to make the positive utility. So from this example, we can say information brings values by getting to a better decision. Thus, a natural question is about, will full revelation be the optimal revelation strategy? The answer is not, and based on our theorem, only reveal whether Q is greater or equal to 2/3 is the optimal revelation strategy. And notably in here, this greater or equal to format is not a coincidence. Actually, we proved there always exists a threshold revelation mechanism, which is the optimal revelation mechanism. So next question is about, when we're talking about optimal mechanism and mechanism design, a critical question is about what mechanism space are we considering. In this paper, we consider the mechanism space which is sequential mechanisms. This space includes all finite extensive form game between the seller and the buyer. This space also known as generic interactive protocols proposed by Payoff et al. In 2012. And in selling information, there is a revelation principle, which means when QT are independent, there always exists a one-round revenue maximizing mechanism, which consists a manual of pi-t and pt. In here, pi-t is a signaling scheme with two signals, sigma 1 and sigma 0, where sigma 0 and sigma 1 result by spiral action 0 and 1 respectively. And pt in here is the payment from the buyer of type t. And we want to emphasize that our mechanism can be generalized to the situation where Qt are dependent. However, our mechanism will only be optimal in the space of one-round mechanisms. Notably, this generalization is not as strict as we might think about, because when QT are dependent, the buyer's belief of the distribution Q will become GQT instead of the same Q, GQ. So the next question is about how do we sell information? We sell information through signaling scheme, and in here we define PyQt as the probability of recommending action 1 given Q and T. We made an assumption on the utility function where VQT equals to V1Q times T plus ρQ. This assumption is widely used in many literatures in cell information, and we show at the end of this paper we can generalize VQT to any generic function with technical assumptions. So next part is about the threshold mechanism. Recall in the previously long example we have VQT equals to QT minus 2. And in here, V1Q equals to Q, and ρQ equals to negative 2 over Q. So recall the definition of signaling scheme PyQt, which models the probability of recommending action 1 given Q and T. We are ready to give the definition of threshold mechanism. A mechanism PyQt is called a threshold mechanism if there exists a threshold function theta t, such as for any t, if ρQ passes this threshold theta t, we will set PyQt equals to 1 and zero otherwise, which means we will recommend action 1 if ρQ passes the threshold and action 0 if ρQ didn't pass the threshold. And the next part is the virtual value. Recall the definition of the lower virtual value, which is the classic virtual value proposed by Marson. It is lower virtual value t. And we also have upper virtual value, which appears in literature of reverse auction and principal agent. And next we have the mixed virtual value in our paper. So the formal definition of mixed virtual value will be take c fraction of the lower virtual value and 1 minus c fraction of the upper virtual value. Denote phi c plus t as the iron version of this mixed virtual value. We propose a lemma which may be of independent interest, that is, the iron version of mixed virtual value is non-decreasing in C. Next, we are ready to give our mean theorem. Our mean theorem divides all instances into 3 cases, and because they have similar structures, I will emphasize the first case. And for the second and third case, they only differed by the threshold signaling function theta t and the payment function. First, let's see the classification. The classification is done by 3 constants, Vt2, Vl, and Vh. The definition of Vl and Vh can be found below. However, we only need to understand they are constant. So given an instance, those constants are easy to be computed. And for example, if Vt2 is less or equal to Vl, which means this instance is in the green region, and we can use the optimal mechanism defined in case 1 to solve it. So the next part is about threshold signaling function, and we can say it's only differed by the virtual value, and in the first case the threshold equals to negative lower virtual value, which means if the ρQ passes this threshold, we will recommend action 1, which is the green region in this graph. Otherwise, we will recommend action 0, which is the red region in this graph. Recall the definition of VQT equals to V1Q times T plus ρQ. If the seller always wants the buyer to make the right choice, the seller will actually recommend it based on T. However, it is proved to be not optimal in our paper. And the next part is about the payment function. The payment function is mainly used to ensure IC, IR, and obedience constraints. The proof of this whole theorem is intricate. So for the interest of time, I would like to highlight 3 major steps. The first step is problem formulation. We formulated our problem as an optimization problem, where we are trying to maximize the revenue with functional variable PT and PyQt. The constraints is first IC constraints. The IC constraints can be reduced to this standard format. However, notably, in selling information, if the buyer misreport another type T, the recommended action may no longer be feasible, so we need a reduction to reach its standard IC constraints. The IR constraints is defined as following. The payoff by participating in this mechanism minus the payment should be at least payoff without participating in the mechanism. And the obedience constraints can be reduced to a similar inequality. And by observation, we can find that if we have payment non-activity for all type T, IR will imply obedience constraints. And we actually proved the lemma that there always exists an optimal IC-IR mechanism where the payment is non-negative for all type T. And the next part is about look at the IR constraint. The payoff by participating in the mechanism will be the expected utility by following the mechanism. So the key difference between selling physical goods and selling information will be when selling physical goods, the payoff without participating in the mechanism will be 0. However, in selling information, the buyer has an outside option, so the payoff without participating in the mechanism will be the max between 0 and VT, where VT is the expected utility of action 1 without any extra information, which means when the distribution is good enough, the buyer will take action 1 without purchasing information. Thus, we want to use a surplus function st to capture the gap between the left side of IR constraint and the right side of IR constraints. And obviously, we want st to always be non-negative for all type T. Now, let's visualize it. So in selling physical goods, when the ST curve is 0 first, and after the buyer got the item, the ST curve will increasing. However, in selling information, we proved that the ST will first weakly increasing from T1 to T bar and weakly decreasing from T bar to T2, where T bar is a type that will derive 0 utility when always making action 1. And with this lemma, we can say the next lemma is that an optimal feasible mechanism must have either st1 equals to 0 or st2 equals to 0. An intuitive way to understand this lemma is that if there is a strictly positive surplus, we can freely transfer this surplus to the revenue of the seller without hurting any constraints. Thus, in the graph, it will be move the ST curve down until one of its ends reach 0. Now we are ready to characterize the feasible mechanism. We can characterize the IC constraints with the first two formulas and characterize IR constraints with those two inequalities, and the obedience constraints is equivalent to payment non-activity. So we can derive the revenue function from IC1 and IC2, and we will get the following revenue function. By observation, we can find that GQ, FT, V1Q are all positive. So the way to maximize the first term is to point-wise maximize it by setting pi qt equals to 1 if and only if rho q is at least negative lower phi t. The way to maximize the second term is to set ut1 equals to 0, and which means we set st1 equals to 0 because 0 is the minimum possible value of ut1. So in the graph, it will be the following. If the ST curve is in the shape of the first graph, the mechanism we build is optimal and feasible. However, if the ST curve is in the shape of the second graph, the mechanism is not feasible because we have some negative ST, which means the IR constraints are violated. So how to fix it? We will derive the revenue function from another point. In the first revenue function, we expand it from T1 point. So in the second revenue function, we expand it from T2 point. And the way to maximize the first term is the same. And the way to minimize the ut2 is to set ut2 to its minimum possible value, which is vt2, which means we set st2 equals to 0. So if the ST curve remains in the same format, we successfully adjust the mechanism to be a feasible mechanism. However, it is possible that if we pin down the IST curve from T1, we lost control of T2. If we pin down the IST curve from T2, we lost control of T1. So how to solve this question? We can say a linear combination of those two expressions produces the same revenue. This is why we have the mixed virtual value, which takes safe fraction of lower virtual value and 1 minus safe fraction of upper virtual value. And in here, C is carefully picked to guarantee the feasibility of the mechanism. And the feasibility proof is quite technical due to feasible constraints and irony, but we can understand it from graph. So in graph, after taking the linear combination, we will get ST in this format. This format has an important property that by moving this curve down, we can reach ST1 equals to 0 and ST2 equals to 0 simultaneously. So thus we can derive the optimal feasible mechanism. The reason they will arrive 0 simultaneously is because the C is carefully picked to guarantee the feasibility of the mechanism. Thus, to wrap up, we proposed closed form solution for the optimal mechanism in solving information. Also, we showed the threshold revelation mechanism is the optimal revelation mechanism. And the last one is that we give formal definition of the mixed virtual value, and we proved its irony property, which may be of independent interest. Thank you, and any questions are very welcome.